Hello, and welcome to Agrosive Physics. Today is day 118, and what I'd like to discuss today is an equation for electrical power. Now, if we go back to our notes from the power and work section of the course, we had an equation for power, which was work over time. So it was the amount of work that was done in a given amount of time, and the unit for power was the watt. Now, in electricity, we can have energy being expended, and the rate at which work is done is known as the power again, and we measure the variable in watts as well. But you're not going to necessarily have work in the specific joules capacity, nor will you have time. In a circuit, everything works almost simultaneously as the electrons are everywhere in the circuit. The entire metal has valence electrons on its outer shell, and the electrons will flow at any point in the circuit. It's not like we start at the beginning, a start line, and then have the electrons run through to the end. In this case, we have electrons constantly throughout the metal, and they're just being pushed through. So at any given instant of time, as soon as we turn on a circuit, we're going to have current flowing, we're going to have resistance in the circuit, and that push caused by the battery or the power supply is going to supply that reason for the electrons to move. So the standard variables that we had when we talked about energy and work and power won't apply in this case. But we can find that the equation simplifies using variables that are common to electricity. Now, many of us are used to the term watts when we talk about light bulbs. A larger watt light bulb will typically be brighter. And when we plug it into our wall outlets, that's the case. If you have a 100-watt bulb, what you're going to do is have a brighter bulb than a 40-watt bulb. Night lights may be 5 watts, they may be 3 watts, they may even be up to 10 watts. You may have a reading lamp that maybe has 20 watts worth of power. And what that is doing is telling you how much energy is being used in the circuit every second. So the unit is still watts, but the way we're going to calculate that is slightly different. In fact, what we have is an equation based on voltage and current. So the equation for power in terms of electricity is P equals VI. Now I'm going to show you how that is derived on the whiteboard a little later. But for now, our equation is P equals VI, and that's our standard equation for power in an electrical circuit. Voltage times current, so volts times amps, will get us watts. And I'll show you where the work over time actually comes from. And as a little hint, if you remember from the current discussion a few days ago, I equals Q over T. There's a T term in that equation, and that's going to help us bridge between the P equals W over T and the P equals VI that we have now. Now, of course, in some circuits, we'll find that you know the voltage and the current, and you could just multiply the two. But in other situations, you may not have voltage or you may not have the current. And what you need to do is have different variables that also equal power so we can find the watts in any situation. It's just like when we went back to the beginning of the course and we had the big 5 equations for kinematics. Those equations were needed so that we can apply them to any situation that we were given variables for. And the 5 equations allowed us to solve for any situation that came up. The same thing applies here. P equals VI is our standard equation, but if we don't have the voltage, what happens is we can combine that with V equals IR, solve for the voltage, and substitute that into the equation. Once again, I'll show you that on the whiteboard later. But what you end up getting if you remove the voltage is P equals I squared times R. Subsequently, if you don't have the current, you can replace that in the circuit using V equals IR, and you end up getting V squared over R. So the power equation has 3 versions. P equals VI is the first, and that's the standard version. It's just the simple 3-variable equation. P equals I squared times R, and P equals V squared over R. Each one of these equations will get us the power in watts, and we'll be able to find the power output of the circuit or the component in the circuit. Many appliances that you may buy are listed in power output. I have a toaster oven that lists it as 1200 watts of power. You could have a dryer, a washing machine perhaps, maybe an electric oven. a microwave oven. Those will all be listed as power outputs, assuming you plug it into a wall outlet. Of course, the dryer is going to be plugged into a slightly different wall outlet, which provides 220 volts of voltage. It needs a little extra push in order to provide the service that it's providing, which is to dry the clothes. Most other appliances, like a coffee pot or a toaster oven, or even a microwave oven, when you plug them into the wall outlet, it's a standard outlet, and that provides 120 volts of push. So in each case, we can find either the current or the voltage or the resistance if we know the power output. And of course, if we're plugging it into the wall and it's listed in power, we're going to know P and we're going to know V. So if we know P and V, we can solve for R or we can solve for the current. Current's important because what it's going to do is provide us a measure of whether or not the circuit may trip. Now, in most people's basement or somewhere in their house, they'll have a circuit breaker or a fuse box. Now, that's to protect your house from burning down. And what it does is it will turn off a circuit if it's drawing too much current. If you have a short circuit, for example, if someone were to happen to connect both ends of the outlet together accidentally, maybe there's something wrong with the plug or there's a stray wire somewhere, what that's going to do is produce very low resistance. And if you have very low resistance, what's going to happen is that's going to increase the current. Remember, the wall outlet provides 120 volts of push. If you have a really low R with V equals IR, that's going to provide a very large I. So if you short the circuit out, it provides a huge current flow. And what that will do, if you don't have a circuit breaker or a fuse box in your house, it will allow too much current to flow. And you could actually melt the wires in your wall and possibly burn down your house. What will happen is your insulation will catch on fire after the insulation on the wire melts, and then you'll start a fire in the wall. And it's very difficult to stop a fire in a wall. You may not even know what's happening right away. So the circuit breaker will turn off if it reaches more than 15 or 20 amps typically of current. And most wires can handle that type of current flowing through it. If you exceed that, that's when trouble will start. Now, that's a measure of the power. We also have a way to figure out the energy in the circuit. Now remember, power is the amount of energy that's used every second. It's the joules per second in an electrical circuit. So if we think about power having the watts equation unit, which is joules per second, if we multiply that by the number of seconds, well, that's going to tell us the energy of the circuit. So it'll tell us how much joules of energy are being used by that particular circuit or the component in the circuit. Now, the energy will allow us to figure out how much money we're going to have to pay the power company at the end of each month. So in order to find the energy of a component or a circuit, what you can do is multiply power times time. Remember, joules per second times seconds will get us joules. Now, using the three versions of the power equation, that means we can find the energy doing VIT, or I squared RT, or V squared over R times T. Each of those three equations that we had for power can be just multiplied by time to figure out the energy that is being used. And what you can do is determine how much energy is used in a day, or a week, or a month, or a year. And when many people buy televisions or refrigerators or any appliance at this point, they all have listed on them how much energy a typical person will use in a year and how much that will cost. A lot of appliances that are under a certain threshold are rated with the Energy Star rating, and that means that they require less energy to run than others. So even though they may be more expensive initially, over the lifetime of the appliance, you'll end up saving money. And on most of these, there's usually a yellow tag on most of the appliances in the store. It'll list what the power output is and how much energy is used per year, and then possibly even how much money it will cost to run. And that's by using it for typical values. For example, televisions might be listed at 3 or 4 hours per day. A light bulb may be listed for a few hours per day. If you use it more often, or you have a higher brightness setting on, for example, a television, you're going to require more energy. But what we can do is find the energy by using E equals PT, or E equals VIT, I squared RT, or v squared over r times t. Each of those equations will allow us to find the energy of the circuit. Now, because those values are going to be quite large because we have to deal with seconds, the power companies have come up with this new variable that is a conversion to make the numbers more manageable for people. So when you deal with the electric company at the end of the month, you're going to be paying per kilowatt hour. Now, a kilowatt hour is how much energy is needed to run 1,000 watts, a kilowatt, for 1 hour. Now, 1,000 watts is 1,000 for P, and an hour is 3,600 seconds. Remember, 60 minutes times 60 seconds is 3,600. So what you have is 3,600 times 1,000. So 3,600 times 1,000 ends up getting us 3.6 times 10 to the 6 joules is a kilowatt hour. And that could be used to make a conversion to find the kilowatt hours, and then the electric company or power company will charge you a certain number of cents per kilowatt hour. And what we'll do is a couple of sample example problems dealing with kilowatt hours, dealing with power, and dealing with energy. But in either case, being able to find the value in joules is important for us as scientists, but the general public does not like dealing with exponents. So any numbers times 10 to a power are something that most people will balk at. They'll be quite frightened to see numbers of times 10 to the 9 or 10 joules. So the power companies use kilowatt hours because they're usually in the tens, 20s, or hundredths of kilowatt hours per month. And that's a much more manageable value for the general population to handle. Remember, by knowing exponents in scientific notation, you know numbers that aren't very scary for you, but may be scary for people who are not used to using exponents. Now, at this point, what we'll do is we'll call it for today. We talked about the power equations, the energy equations, and a conversion from kilowatt hours to joules in terms of energy. Well, that's it for today, and I thank you. Now, if you recall from our previous chapters, we had an equation for power when we talked about work, and it was the rate at which work was done, so it's work over time. Now, we also have our new, most versatile equation of all, which is V equals IR. That's a new equation. We have I equals Q over T, also a new equation from this chapter. And if we go back one chapter, if you will, for static electricity, we also have our equation for potential in a circuit, which is W over Q. Now, what I'd like to do is relate, instead of a mechanical power equation, relate it using the electrical versions of our equations, our variables that deal with electricity. Now, the first thing I want to do is solve for W in this last equation, which would be W equals VQ. Now, the reason I'm going to do that is because I'm going to take this W and replace it right there. If I do that, my equation for power becomes VQ over T. Well, that equation right there can further be simplified because Q over T, if we remember right here, is I. And this becomes P equals V I. So our equation for electrical power is voltage times current. But what you'll find is that some problems don't have voltage or don't have current, or some problems only have resistance. So what we can do is use our versatile equation here to eliminate the variable that we may not have. For example, if we don't have V, we could replace IR for V, which would be IRI. Well, instead of having two i's, we just replace it as I squared times R. Now, maybe we don't have the I, and we want to replace that. So if that's the case, we'll divide this by R. We'll replace the I with V over R. Well, instead of having two V's, we'll just turn it into V squared over R. So our power equation actually has three forms. It's P equals VI, P equals I squared times R, and P equals V squared over R. So we have three different versions of the power equation. The units are always in watts. And watts is going to be a very useful term for us in electricity because many of our components are listed as watts. When I did the toaster problem the other day, the actual value listed on the toaster was not in ohms. It was listed in watts. It was listed as a power. Light bulbs are listed in watts. And other devices, such as even a microwave, can tell you the total power output that the microwave can produce when operating at full power. Now, with our new equation, what we can do is also realize that if we remember that watts is joules per second, because it's work over time, if we multiply the power times T, so times seconds again, we're going to get J alone, which would be the energy. So what we have is our secondary equation, which is E. The energy in an electrical situation is power times time. So power, which is joules per second, times seconds, you end up with joules. That means you can just put a T at the end of each of these terms. You have VIT, I squared RT, or V squared over R times T. And that will get you the electrical energy. Now, the electrical energy is going to be useful when we talk about kilowatt hours, and we'll discuss that in a moment. Now, the kilowatt hour is a unit of energy. And what it can do is simplify the numbers used when using electrical devices. For example, it represents how much energy is used when we have 1,000 watts on for an hour. So that could be 10 100-watt bulbs or one 1,000 watt bulb. If we keep it on for 1 hour, how much energy does that use? So the power, and if we just use our PT equation, power is 1,000 watts. Remember, kilo is 10 to the 3. And the time is 1 hour. Now, the biggest problem we have in this course is conversions, and that's typically what my students struggle with all year. So one more time, how many seconds are there in an hour? Well, if you need to go through the process, here's it one more time. 1 hour. 1 hour is 60 minutes. And 1 minute is 60 seconds. So the minutes cancel, and we're left with 60 60s. 60 times 60 is 3,600. So we end up with 3,600 seconds. So if you multiply those two numbers, 1,000 times 3,600, you end up getting 3.6 times 10 to the 1, 2, 3, 4, 5, 6 joules. So that value is what we call 1 kilowatt hour. And most of the time, you'll be charged for your electric bill based on the number of kilowatt hours that you use. Many people would balk at numbers of 10 to the 6 or 10 to the 9 or 10 to the 12 joules. So the electric companies know this, and they want people to be more comfortable with their numbers, so they convert them to kilowatt hours, which are in the tens or hundreds at the most. And what you'll see is many electric companies will charge you based on a number. So let's just call it 11 cents per kilowatt hour. So if you use 1 kilowatt hour, it costs you 11 cents. 2 kilowatt hours, 22 cents. And you can use that as another conversion. In fact, I've used light bulbs that list average cost to use it. Many objects are Energy Star rated, and they have the average cost. And that's based on turning the device on using a certain amount of kilowatt hours throughout the year. So the kilowatt hour is a useful conversion. And once we know the kilowatt hours, we could convert it to money if we know how much the electric company is charging per kilowatt hour. So the kilowatt hour is not a power unit. It is a unit of energy. And that's something to watch out for. Remember, we did electron volts, which was not a measure of voltage, but a measure of energy as well. So we have these conversions that help us deal with numbers that are much more reasonable than our regular everyday numbers that would be scientific notation. So that's the kilowatt hour.